Switching subjects, sorry. First, a few little brief announcements. I sent this out earlier. I'm really sorry. I am just getting hammered this week, so I'm a little bit behind. I have all our materials are mostly ready to go, but what this has meant is that today's been a little nuts, and the rest of this week will probably also be a little nuts. So my troubleshooting for Seagal is going to take longer than I was hoping, but it's in the works, and I will hopefully get that out soon. I also did mention that, and I'll try to get an updated version of the homework where if you decide that you would like to not do the Seagal coding, there's an alternative where you will read a paper that uses Seagal and write a short summary of it in a kind of astrobyte style. So I think this would be a really good thing. I'm going to open it up for everyone, but I think if you're more interested in, science communication and writing, disseminating science to a broader audience than you are in potentially going a track where you'll be doing a lot of research and coding, this might be a better fit for you, and so I'm totally fine with you doing that instead. And then you don't have to worry about trying to install Seagal, which will be one less headache. But I don't want that, again, I don't want you to spend too much time on that. So I want to find ways to make that easier and not have you guys bash your head against it for hours, because that's not the point of that activity. The second part everyone still will need to do and just uses Anaconda. We will do a practice version next class. On that note, next class, Andrea will be observing me, so she will be in our Zoom session, I think is the plan. I haven't actually checked, but that was our plan last time we talked. So she will be here watching me. She might ask you all questions. I know you all know Andrea, so I don't think that will be stressful or scary, but just as a warning that she will probably be in our Zoom session next class. And that again, she will be watching me, not watching you, so it's nothing to be concerned about. But if she asks you a question, you should respond because it's Andrea. The other one little thing I want to point out before I get started, in our activities today, if you haven't yet had a chance to download this file, I would download it now, so when we start actually doing the coding, you don't have to wait for it to download because it's a bit bigger than the typical images we work with, and that's because it's a cube, which I will talk about what that means. On the same note, kind of last minute, I updated these two notebooks. So if you did download those early and were good and downloaded them early, they've changed in the past hour, only slightly, but then you'll want to re-download those because they'll be updated versions. Okay, I think that's what I wanted to say to start. Any questions on my ramblings? Okay. Let's do some science. So today we're going to be focused on galaxy rotation curves and how we can measure rotation in galaxies, get information from that by looking at the width of different spectral features. So essentially, we look at spectral features and see how across a galaxy and see how they're either blue shifted or red shifted and use that to figure out how fast the galaxy is rotating. So we'll be doing some of that as well as looking at how rotation in different parts of a galaxy might inform us about the composition and properties of different parts of a galaxy. So that's basically my plan for today, and then we'll end by actually measuring rotation of NGC 7331, which is what that notebook will walk you through. So first, a little bit of historical background. So again, like I said, we can use spectra to measure velocity shifts across the disk of a galaxy by looking at how one spectral line is either red shifted or blue shifted at different edges of a galaxy. For most of today, we will be talking about spiral galaxies, which has been kind of true for like 90% of this class, since spiral galaxies have organized rotation and elliptical galaxies don't. So when we talk about rotation, we're usually talking about spirals. You can still measure velocity shifts across ellipticals, but that's going to be more of a velocity distribution than it is going to be a straight rotation curve because ellipticals aren't rotating. So to get ellipticals masses, you have to do slightly different things, and we will talk about that a little bit at the end. These measurements of rotation were first done with M31, the Sombrero Galaxy, so that one that looks kind of like a sombrero, as well as Andromeda back in the early 1900s. In order to get nice measurements of rotation, you need disk galaxies that are sort of edge-on. So if you're looking at face-on galaxies, you're not going to see that redshift, blue shift, so you can't do this kind of rotation measurement. So the Sombrero Galaxy, where you're seeing it pretty much directly edge-on, is a great candidate. Andromeda is pretty close to edge-on, and it's close, which makes it easier to look at. Kind of amazingly, back in the 1940s, Oort, who the Oort cloud is named after, noticed that the distribution of light did not match the distribution in mass based on rotation. So that was kind of the earliest indication that there was some dark matter in galaxies. So mass that does not generate light is dark, and it has mass, so it is matter, so dark matter. And then in the 1960s, this was confirmed by Vera Rubin, who's in the picture, whichever direction we need to go. Using the Kitt Peak Observatory, she measured rotation curves for many galaxies and noticed that, again, the starlight did not match the distribution in mass, which pretty much confirmed that there was dark matter in galaxies. Yeah. So that's kind of history. Now we can think about how we're doing this today and what we can learn from those rotation curves. So the first thing that I want to just mention, as we're going to break up our galaxy into a few different chunks, as we have done throughout the semester, because different parts of a galaxy will rotate differently. So how the bulge rotates, how the disk rotates, and how objects in the halo rotate will tell us different things about the galaxy. So to kind of show this, I've pulled up, let me set this all back to 0. I was playing around with it. So this is just kind of a model showing that. So the red points here are data, and we can adjust the amount of mass in different parts of the galaxy with these sliders to try to get a velocity, a rotation curve that will match this data. So here we have radius versus velocity. So if we add a point mass, we can see we get kind of Keplerian motion around the point mass in the center. So that's kind of going to be the supermassive black hole in the center of a galaxy. Obviously, galaxies are a lot more than just the supermassive black hole in the center, so a point mass alone is not a good model for a galaxy. If we then add a star disk, we can start to get something that looks a bit more right, but we can see that there's this kind of decrease in the velocity at large radii that does not match the observed curve. So in order to get that to match, we need to add a dark matter halo and just kind of fiddle around with these things until you get something that looks about right. So the point mass is going to mostly dominate the rotation in the very, very, very inner parts of the bulge. So that's our supermassive black hole. Stars are going to mostly dominate in the inner parts of the disk, and then the dark matter halo will take over as we get to the edges of the disk and into the halo. So depending on what part of the galaxy you measure rotation for, you will be measuring kind of the effects of different parts of the galaxy. And I will add this lecture to our presentation file, which I think I put in our course slide or course homepage. So if you want to play around with that yourself, you can do that afterwards. It's kind of fun. So the first part I want to talk about, is the rotation in the central bulge. This is what's going to be kind of dominated by the supermassive black hole in the center of each galaxy. But in order to measure that actual rotation caused by the black hole, we need very high resolution spectra, because the black hole will only dominate on the very, very inner parts of a galaxy. So this is kind of showing that, like, if we do want to see the uptick in the galaxy's velocity distribution, rotational velocity caused by the black hole, you need to observe that galaxy, the center of the galaxy, the central region, of about 0.001 to 1.1 kiloparsecs, which is very, very difficult to do, and we can really only do with the closest galaxies. So for example, the Virgo cluster of galaxies is about 20 megaparsecs away. What would be the angular size of a 10 parsec region around the center of a galaxy in the Virgo cluster? So we can figure that out. Just quick. So this is kind of using, oh my gosh, if I can draw a straight line, that would be helpful. So if we have the distance, so we are here observing a galaxy in the Virgo cluster, a beautiful galaxy that looks only slightly like a spider, which is at a distance of, that is supposed to be a D, I'm sorry, 20 megaparsecs. And we want to know the angular size of this central 10 parsec region. So the angular size at 10 parsecs. So what is this exaggerated angle going to be? So we can see that that's kind of, you can use either your small angle approximation or you can use tangent. So it's going to be the inverse tangent of 10 divided by 20 times 10 to the 6th, or about 4.99 times 10 to the negative 7 radians, which is the equivalent of approximately 0.1 arcsecond. So even for the most nearby galaxies, we would need a resolution of 0.1 arcsecond to image a 10 parsec region around the center. And to measure the effects of the supermassive black hole in the center, we need something more like the resolution of about a point of 0.001, so even 1 parsec instead of 10 parsecs. So getting these measurements is very, very, very tricky and can only really be done with galaxies that are very, very close. But when we can get them, and there are some amazing resolution spectrometers out there, especially the ones that are looking for planets. So if we can take one of those and turn it towards a galaxy for a few hours, probably, I don't know the exact observing time, you might be able to actually measure this rotation. And from that, you can get an idea of the mass of a supermassive black hole in the center of this galaxy by using Kepler's law to estimate the mass of the black hole in the bulge, which will be the dominant mass in the bulge. I'm going to do one of those calculations, but before I do, does anyone have any questions about the angular resolution stuff I just did? Or anything else? Sweet. I'm gonna go ahead and erase that then, unless I hear any screams. Oh my gosh, and if I can use my mouse. There we go. Okay. So we can do this, of course, for the Milky Way. This is one of the easiest galaxies to do it for because it is the one we are in, so we are closest to the central region. So this is, I showed this to you on, I think, the third day of class, but these are those 15 years of measurements of the stars going around the supermassive black hole done by Keck. And if we look at this guy right here, this yellow star, we can see at around 2011, it made one complete orbit around Sagittarius A star. So using this scale of 0.1 arc seconds, I kind of estimated that this was about 0.2 arc seconds that it traveled in the 15 years. So from 2000, I got 11.3 was when it finished. It starts at 1995.5. So in a period of about, a little more, about 15.7 years, that star has made one complete orbit around Sagittarius A star. So we can get, maybe I'll try typing this time to make it slightly less painful. We can use Kepler's law. So P squared is equal to A cubed over M plus M, let's say M1 plus M2. So that's our kind of Kepler's law when we are in solar system units, so years and solar masses and AU. A little note, so M1 is going to be the mass of the supermassive black hole, or Sagittarius A star. M2 is going to be the mass of this star that made its rotation around it. Because Sagittarius A star is the dominant mass in this system, we can say M1 plus M2 is approximately equal to M1. So the mass of the star plus the mass of the black hole is approximately equal to the mass of the black hole. So we can rewrite this as P squared is equal to A cubed divided by M1, where M1 is again that mass of Sagittarius A star. So with a little bit of approximation, I said A was equal to, if this total distance, if my major axis is about 0.2 arc seconds, my semi-major axis is 0.1 arc second. The center of the Milky Way is about 8.3 kiloparsecs from us, so we can multiply by 8.3 kpc to get, because we're working in kiloparsecs and AU, I don't have to convert. This is like parallax shifting again, so all that conversion happens in the math that I'm not doing here. So I get A of 0.83 kilo AU. So again, kind of like parallax, D is theta over big D. Sorry, trying to think the best way to explain this. Because we're working in arc seconds, parsecs, and AU, I'm skipping some conversion steps. Does that look semi-familiar to folks? Okay. So I can go ahead, we can plug that in and solve for M. So M1 should be equal to A cubed divided by P squared, or 0.83 times 10 to the power of 3 AU cubed divided by about 15.7 years squared to get a mass of, I got about 2.3 times 10 to the power of 6 solar masses. With my little funky calculation, according to our better measurements that are done not with me just kind of estimating based off a YouTube video. The mass of Sagittarius A star is closer to 4.3 times 10 to the 6th M solar, but you know, I'm only off by a factor of 2, so I think that's not bad from just working with this image. So that's kind of how we can use Kepler's law along with the rotation of stars around the center of the galaxy to find the mass of a supermassive black hole in the center of a galaxy, specifically our galaxy for this example. Any questions there? Typically, though, for any galaxy besides our own, we're not going to be measuring individual stars. Instead, we're going to be measuring the kind of velocity of the interior area of the galaxy. So I'm going to go ahead and clear this. So for a galaxy like NGC 4258, what we will instead measure is kind of the rotational velocity at small radii. And we can use this as well to get the mass of the central supermassive black hole in the center with just a few more steps. So we'd have to convert 0.1 parsecs to AU if we wanted to use Kepler's law, and we'd also need to determine the period if the velocity is 900 kilometers per second, but we can of course do that using P is going to be equal to the distance you would have to travel, so the circumference at that radius, so 2 times pi times r, get the r eventually, divided by v, so divided by the speed we're going. So the distance we travel around the center divided by the speed we are traveling as we move around the center. So with this and some conversions, we get that the period of this material we're measuring is about 682 years. Then we can go ahead and use Kepler's law again. So without doing as many steps, it's again going to be the mass of the supermassive black hole in the center is going to be approximately A cubed divided by P squared when we work in AU and years. So we would need to convert that R, so 0.1 parsecs times 206,265 AU per parsec to the power of 3 cubed divided by 682 years squared to get a value of approximately 1.88 times 10 to the power of 7 solar masses. So again, just using Kepler's law, but with the additional step that for a typical galaxy, we're not measuring the rotation of an individual star. We're instead measuring the velocity based on Doppler shifts, which we will get to as well. I'll show a few examples of that. But from that, we can get an idea of the mass of the central supermassive black hole in the center of nearby galaxies, at least. Before we move it out to the disk, does anyone have any questions about the bulge and measuring the mass of the supermassive black hole with velocity? Seeing some head shakes. Okay. Go ahead and erase this then. We're gonna keep moving right along. So the next part of the galaxy we might be interested is the disk. interested in is the disk. Again, we're talking mostly about spirals because ellipticals don't have this nice organized rotation. The great thing about the disk is it's bigger than the central bulge, so it's easier to measure the rotation of the disk just because you don't need as good angular resolution to get nice precise measurements. Disk is extended, so it's going to be 10 to 20 kiloparsecs as shown here. This is also where the stars and the gas are, so the things emitting light are in the disk, so we can actually measure them for the most part. There are stars in the halo, there is gas in the halo, it is just more diffuse, so it is harder to measure. Disk velocity, especially in the interior parts, is dominated by stars, but we can also use any perturbations from a kind of nice rotational model to start understanding the dynamical history of the galaxy. So a kind of typical galaxy will have a velocity curve like this one shown here for NGC 6503, where we see the points are going to be the measurements, and then we're fitting a few different components. A disk of stars, where we're seeing in the center where the stars are more concentrated around the bulge, there's kind of a peak, and then as there's fewer and fewer stars, we would expect velocity to fall off with radius. So as you get further from that kind of central concentration of stars, you should see the velocity fall off. That's not what we see, of course, because there's a dark matter halo. So you have to add in a halo component. And then there's also some velocity caused by, or some rotation caused by the mass of gas, a not insignificant amount. So by adding these three components together, we can model the actual rotation of galaxies and get an idea of the different components and how much mass is in each component. But this is a kind of nice organized disk, what we would expect. Not all galaxies look like this. Some galaxies have some weird bumps and curves and just craziness going on that might indicate past interactions with other galaxies. So if you get close enough to another galaxy, that might disturb the rotation. If you do go through a collision, that could also disturb the rotation, which is what happened with NGC 3593, which is the galaxy I'm showing here. And what they noticed in this galaxy is that when you measure the rotation of the stars, you see this velocity curve. So one side moving towards us, one side moving away. But when you measure the velocity of the gas, you see this velocity curve. So the gas is rotating in the opposite direction of the stars. So this is just kind of a crazy example of the different types of rotations you might measure in a galaxy. And what this suggests is very likely NGC 3593 went through a collision at some point with a galaxy rotating the opposite direction. So when these two galaxies collided, the gas got all mixed up and is still rotating backwards from the stars. So we're seeing the leftover impacts of a giant collision between two galaxies by looking at the weirdness in the rotation of the disk. Not always is it this kind of insane. Usually it's just kind of bumps and wiggles that you might not exactly expect, but we can get an idea a bit about the dynamical history of a galaxy by looking at the rotational curve in the disk. We can also use those models to get kind of an idea of the makeup, how much is stars, how much is dark matter, and how much is gas. Any questions there before we talk about dark matter? I think that's the next slide. Do know my plan. Okay, so the next thing we can look at rotation of is the dark matter, is the halo, and this is where we are very dominated by dark matter. So typically, in order to measure the rotation in the halo, you might look at the 21 centimeter line of neutral hydrogen. And that's because this line is, the hydrogen gas is going to be extended throughout the disk. So the halo rotation, we're still kind of looking at the disk, not the actual halo, but we're getting an idea of the really outer parts of the disk, measuring the furthest edges of the disk using the H1 21 centimeter line, which is long enough that you don't have to worry about dust absorption. So we're way far in the radio. There's no absorption from dust because this is a long wavelength. It can just bust right through. So we can measure the H121 centimeter line through across the disk and get a good idea of how things are rotating in different parts of the disk by measuring the shift of the 21 centimeter line depending on where you look. Based on these measurements of and that's what we will be doing later today, so you'll get to see this a lot more. Sorry. Based on the measurements we see with the 21 centimeter line, this is where we start getting into this dark matter, because there are not enough stars to produce the large rotational velocities measured. So I like to think about dark matter. People will argue with me. I think how you think of dark matter is a little dependent on who you are, but I like to think of dark matter as almost an observation. So what dark matter is a theory. Dark matter itself is an observation, because we look at galaxies and we measure the amount of light and we measure the amount of mass. And there is some amount of mass, there is some amount of matter that is not interacting with light and is therefore dark. So we observe dark matter. We observe matter that does not interact with light but has mass. One of the ways we do this is by looking at galaxy rotation curves. Some people will get frustrated with me for calling it an observation and not a theory. I get frustrated with people who like to say that dark matter might not exist, because I think we are pretty dang sure at this point that dark matter exists. But that's a little tangent with my own frustrations of talking with people who want to argue about how good our observations are of dark matter. It's like we have like 10 ways of showing that dark matter needs to be there. So it probably is. We can argue about dark energy. Dark matter seems to be fairly solidly there. Again, sorry, one of my weird little soapboxes. So based on these measurements of the rotation in the edges of the disk, we notice that there is too much mass for the amount of light that could be produced by stars, and again, therefore must be dark matter. So as I said, dark matter is the extra mass that does not interact with light, either through absorption or emission. So there's no, it can't just be dust. It can't just be things that don't emit light there by themselves, because it also does not seem to absorb light. But it must be there based on these rotation curves, and there must be a whole heck of a lot of it compared to everything else. By measuring how much galaxies rotate and fitting those curves to get an idea of how much mass must be in the halo, we can put constraints on the type of dark matter that might be in galaxies. So some things that you might consider or might hear about, you can hear about self-interacting dark matter. So dark matter does not interact with normal matter, but it might interact with other dark matter particles. So that would be self-interacting dark matter. You might hear the terms cold, warm, or hot dark matter, and that has to do with the speed of the dark matter particle, so kind of the temperature. We think for the most part, cold dark matter models do the best job of modeling how galaxies rotate, just because if you have a dynamically hotter system, when galaxies collide, that changes how the dark matter will interact, the dark matter halos of the two galaxies will interact, and that's not what we see. There's also kind of two popular theories about what dark matter might be, or the macho dark matter theory. So massive compact halo objects are machos. We are pretty sure that is not the case, because we think we would observe them in our own galaxy. So this would be like a lot of planets floating around in the halo, just unassociated planets. We don't seem to see that. We think we would detect it with our detectors so far. So machos are probably not correct, but still get thrown out on occasion. Another popular model is the weakly interacting massive particle, or the WIMP. And this is a particle. If you take particle physics, you'll talk about the W and Z bosons, so the particles that moderate the weak force. So it's a particle that has the same mass and cross-section of the weak particle, and it seems to kind of, when you plug it into some complex equations about complex cosmology equations, you get the right amount of dark matter if your dark matter is made of WIMPs. But that's kind of a hand-wavy calculation, and whether or not it's correct. There are other theories about axions and antisymmetric particles and neutrinos, but that is more of a cosmology kind of discussion. I just wanted to point out some of those things here. Based on rotations of halos, we can also get a bit of an idea of the dark matter profile, so how the dark matter halo is kind of arranged. And so for the most part, when you talk about this, you'll talk about core and cusp models. So these are kind of showing the, this would be a core and a cusp model of dark matter. So we have density of dark matter on the y-axis, sort of normalized density versus radius on your galaxy in the halo, again, normalized. But the important thing is that a core model, the dark matter, when you hit a certain radius, the dark matter gets denser and denser until you hit a certain radius and it just flattens out and has a constant density for the interior part of a galaxy. So that's going to be the core model, has this kind of, has a constant density in the interior, and then it falls off as you get further and further into the halo. Whereas the cusp model increases in density as you get into the galaxy. So will be very, very, very dense dark matter in the core of a galaxy, or in the bulge of a galaxy, and then as you go out, it gets less and less dense until you reach the outer halos. So yeah, core is a model where constant density, cusp, you have a spike in density in the center. This is log scale, so it doesn't quite look like that, but that's kind of the two models. This was one of the better graphs I could find showing it. So just an idea of the two different models for how dark matter might be arranged in the halos of galaxies. Based on different fitting you can do to the velocity measurements, either with the H1 gas or with other components of the halo, we can get an idea of which density profile might be a better fit for dark matter, which will also kind of constrain the type of dark matter that is in the halo of galaxies. Despite the fact that ellipticals do not rotate, that does not mean we don't think they have dark matter. We can still measure the halo mass of ellipticals, either by looking at the motion of the globular clusters and kind of making some assumptions about what the mass must be in order for the globular clusters not to go flying off into intergalactic space. So just like planets, when you talk about the escape velocity of the atmosphere in a planet, you can talk about the escape velocity for a galaxy. And you can look at how fast objects are rotating around ellipticals and figure out what the mass must be of an elliptical for it not to lose its globular clusters and halo gases. You can also find the mass of ellipticals using gravitational lensing. So this is, I'm just going to briefly mention it because this is again more of a cosmology kind of class topic, but gravitational lensing is when the light gets bent around a massive source. How the light gets bent tells you the mass of that source. So if there's an elliptical galaxy in between us, and then I am a really distant galaxy, the light from me, the distant galaxy, will get bent around the elliptical. You will observe it, and how it is bent will tell you the mass of the elliptical. So we can, despite the fact ellipticals do not have rotation curves, we can still get an idea of the dark matter in ellipticals. They do also have dark matter halos. So that was a lot of weird theoretical nonsense about dark matter. Any questions there? I can try to answer. Okay. So from measurements of the dark matter halo, we get to something called the mass to light ratio. So this is a pretty common thing that gets referred to for most galaxies. and it's just the amount of mass in a galaxy to the amount of light in a galaxy. And unlike when we talked about SED fitting, this is the total mass of the galaxy divided by the total light from a galaxy instead of the stellar mass divided by the stellar light. So total mass of a galaxy divided by the total light. We usually define the mass to light ratio as the mass and the light within the Holmberg radius. So the Holmberg radius is the radius of an isophote with a surface brightness of 26.5 magnitudes per arcsecond. So this is kind of, we discussed this very early in the semester, but those isophotes are radii of constant surface brightness. So we divide brightness by area. And so this is, if the Holmberg radius will be the surface brightness of about 26.5 magnitudes per arcsecond squared. So pretty extended out in the disk, but it's a way that we can get kind of a common radius to compare different galaxies instead of nearby galaxies having bright, bigger radii or something based on what we can observe. If we then assume a spherical distribution of mass, we can use the velocities measured as well as the radius, the Holmberg radius, whatever that is for a galaxy, to find the mass enclosed in that radius. So for a given Holmberg radius, the mass will be equal to the radius times velocity squared divided by g, which this is just the how we find using the force of gravity. So just using the law of gravity, we can get the mass based on the velocity. So it's setting kind of the setting the orbital velocity, using the orbital velocity equation to predict the interior mass, assuming that it's a uniform spherical distribution. The other thing that's slightly, we then measure the light by looking at the total luminosity within that Holmberg radius. Unfortunately, that depends on the band you're looking at. So the mass to light will be the mass to light ratio for B band, or the mass to light ratio for V band, or the mass to light ratio for whichever band you're actually looking at. Typically, when you say it, it'll be either B or V band, but that's not necessarily always true, and it does really depend on which band you use, because if you use some of those farther infrared bands, you're also getting a lot of light from dust, whereas if you use the light from the B or V band, you're losing light to dust. So it's going to change your mass to light ratio, but depending on which band you use and what type of galaxy you're looking at, you're going to see ranges of about 2 to about 100. So mass to light ratios of 2 to about 100. So, but what that tells us is that there is much too much mass for the amount of stars. So galaxies must be dominated by dark matter. And this is just showing this graph I think I grabbed from your reading, where we're getting the mass to light ratios in different bands, but also for different types of galaxies. So they tend to be, mass to light ratios tend to be higher for lenticular and lower for SD and irregular galaxies. But this is all kind of depends mostly on, you know, the band you're looking at and which ones are dominated by the massive stars that just put out a lot of light. So for galaxies that just are likely to have been going through some amount of star formation, they're going to be brighter because of that. So that kind of throws this off as well. So it doesn't mean that irregular galaxies have less dark matter. It just means that irregular galaxies probably have more bright stars. So still we're getting kind of galaxies are dominated by dark matter, and we can use these mass to light ratios to figure out just how much they're dominated by dark matter. There's also some differences between galaxy types in terms of speeds of rotations. So earlier type galaxies rotate faster than later type galaxies. So even with the disk galaxies, SA galaxies rotate faster than SB and SC, kind of stepping through in that direction. I don't have a good reason why, I just know that this is what we observe. barred spiral galaxies follow similar patterns. In S capital B A galaxies will rotate faster than S capital B C galaxies. But because the gas is not uniformly distributed around the disk, there will be kind of steps in velocity. It won't be a nice smooth curve. You'll see some kind of shifts in velocity along the bar. You'll see jumps in the velocity around the disk that are attributed to the presence of the bar. Irregular galaxies can have some rotation, some uniform rotation, but because they're not nice disks, organized disks, they're generally fairly chaotic, so that makes it slightly difficult to measure rotation the same way we would in a disk. And then ellipticals have little to no organized rotation at all, so they're more just stars all moving around whichever direction they want to be moving. One thing you'll see for galaxies, for spiral galaxies a lot, is people will plot these things called spider diagrams, which is what I've shown here. So each of these lines shows, it's kind of like, you can think of it like a topographic map, where instead of elevation, they've shown lines of constant velocity. So along the disk where the velocity is 690 kilometers per second, that's this line here. And depending on where you are in the disk, you see different velocity. You get this kind of spider-like structure. If your spider is here and has way, way, way too many legs. So these spider diagrams will show up sometimes in papers looking at velocities of galaxies, where you can kind of imagine the reason why this area has the same velocity rate is because we're seeing this disk not quite edge on. So you're seeing two parts of the disk that have the same rotation, just it's been tilted. So if it was a nice, perfectly edge on disk, you would instead see a spider diagram that was a bunch of straight lines. Because it's not edge on, we're seeing kind of the shift where different parts of the disk have the same velocity. The wind's going crazy. So measuring, sorry, that pink line is going to make more sense in a second, I think. In order to measure rotation, we can use the Doppler shift, as I've said, of an emission line across the galaxy. Typically, this will be, typically emission lines that get used to do this are the H alpha line, vibrational transitions of the carbon monoxide line, or of carbon monoxide, sorry, vibrational transitions of carbon monoxide, or that should say H1, not H2, I'm sorry. That should just be H1, the H1 21 centimeter line. Because different lines measure different phases of the ISM, whichever line you choose, you're kind of going to be measuring a different component of your disk. So that's something to keep in mind. If you're measuring the rotation of the carbon monoxide lines, then you're measuring kind of the more molecular gas in the disk and how it's rotating, whereas you're measuring the H alpha line, you're getting the diffuse ionized gas, which might have more to do with the young stars and the more extended disk. And then the 21 centimeter line is just because it can be measured in every part of the disk because there's hydrogen everywhere. It gets a good idea of just the entire rotation system. We can then also, so with this guy, I've got a galaxy here that is edge on. They've put a slit right along the edge of this galaxy to measure the rotation in that galaxy. So what you see with your spectra then, this is our galaxy as a function of wavelength, and this is kind of the slit that you're seeing along there. So galaxy as a function of wavelength, and this is the H alpha line going along that slit. So with the upper, across the slit, you're seeing how the H alpha line is shifted. So the H alpha line has been shifted depending on which part of the disk you're looking at. So we can measure the rotation by looking at the Doppler shift of each of these two arms. So this is the spiral arm on one end, spiral arm on the other end, and then the bulge. Yeah. So we can get an idea of where the rest wavelength of this would be. So this galaxy is going to be redshifted some amount, so the H alpha line isn't going to be quite at 65, 63 angstroms, but it's going to be pretty close. So I found, just kind of by eye, that the rest wavelength, so lambda for this galaxy is about, I said, 6,645 angstroms. So again, so this is 660, this is 6,600, this is 6,650, so 10, 20, 30, 40, 50, about 6,645 angstroms. And then we can get the shift in our wavelength by looking at the difference here. So it looks to me like delta lambda is about 5 angstroms. So with that, we can then use our Doppler shift to get the rotational speed of the galaxy. So with those numbers, I'll let you guys calculate this time. How fast is this galaxy rotating? Either shout it out or throw it in the chat when you have a number. So maybe, 0.075 times speed, the speed of light, so around 225 kilometers per second, or 2,000, oh gosh, too many significant figures, 225,000 meters per second. Yeah, thanks for converting. My brain it's going. It's like the sucking sound by the whiteboard, except I'm just constantly in that. Okay. Anyways, but this is kind of one way. So if you wanted to use H alpha, that would be how you would measure the rotation using the H alpha line. Putting the slit of your spectrograph across the disk of the galaxy. Across the disk of the galaxy, and then measuring how the line shifts depending on where in the galaxy you're looking. For lines that aren't the H alpha line, the arms don't show up just because they're fainter, so you can only see the bulge. So that's why the rest of the galaxy spectra, we only see the bulge, we only see at this radius of 0. But when we get in a brighter emission line, you can start to actually see what's going on. You can also see like some clumps, which might tell you there's star formation happening in little star forming regions along the disk. So that's kind of a cool thing you can also see from this example. So with that, now we're going to kind of use the other option to measure the rotation of the galaxy NGC 7331, which is what is shown here. So that's what's in your notebook for today. So in your assignment measuring rotation, which I did publish, so you should be able to access that. There is a cube called the NGC 7331, which hopefully you have downloaded, as well as 2 notebooks. I'm just going to really quickly show you what a cube is. So a cube is when we get data, not only we get kind of an extra dimension in our image, so we have position as well as radius. That's the header. Where is my? So for a cube, you get this special little extra box when you open it in DS9, which allows you to look at the galaxy at different wavelength slices. So we have kind of nothing here because we are looking at the wrong wavelength. We haven't quite gotten to the slice, sorry, there we go. So I can step through the slices in wavelength. And eventually we start to see something bright show up. So that's one arm of the galaxy is brightest at that bit. And then we can kind of see that spider diagram as we step through the different wavelengths. Different places have different velocities, different wavelengths. Different places within the disk have different velocities. So you're seeing the H1 line shifted as we step through wavelength space. And there's the other side. So cubes are pretty amazing. They just give you a large amount of data. You get both spatial data and wavelength data. So just to play that, you can see you just stepping through where the arms are, how they've been shifted as a function of wavelength, depending on where you are looking. So in order to find out how this galaxy is rotating, we're going to measure the flux as a function of wavelength. So there's going to be some aperture photometry, but as a function of wavelength, as we step through the different frames in this cube, so the different wavelength slices. We will get to play more with these kind of things when we talk about IFU surveys, so in a couple weeks. But this is just one I wanted to throw out there so you could do a measurement of rotation and see how awesome spectral data cubes are. So what you will be doing, let's see if I can pull up the right one. Okay, yeah. There's two versions of this. So this is, yeah, just kind of showing that again. You get a cube is of this notebook where you have like your cube. You can get spectra along different positions within that cube, and it's awesome. So what we're going to do is load that up, and then this is just showing you how you would find the flux from one wavelength slice. So usually when we've worked with FITS images, they've had three dimensions, sort of. So an X, a Y, and then just kind of they've had two dimensions, I should say, an X and a Y. Now we have 4 dimensions. So the first one doesn't matter. We're not going to mess with it. Not important. The second one is going to be the wavelength dimension. And then we have our X and our Y. So wavelength, 116 slices of wavelength, and then 1024 pixels by 1024 pixels. We will be doing elliptical aperture photometry on this galaxy. So just using these ellipses to extract the flux for each wavelength slice. So you can get slices by saying I want to work in the 0th frame, look at the 23rd slice in wavelength. So that's what this is. This is saying the 23rd slice in wavelength. And then you can either use, if you're using AppPhoto, you just put in your data and your elliptical aperture for this one, since we're looking more at an ellipse. Plus, I had some issues grabbing the actual Arian deck. Then, that's prettier. Your goal will be to make a for loop that extracts the flux for every wavelength slice. So I explain how to do that. A for loop is just something where we say we're going to work through every wavelength slice. So we're going to start, we're going to go have for every position within this data cube, for every wavelength slice, we are going to extract a flux, and then we're going to plot that flux, and we're also going to store that flux. And what we should see is a graph that looks like this, where we can see velocity for each of the 2 disks, the edge of the disk, and then also the velocity of the center part. So the spikes are going to be where the disk is, and then the center part will be a little lower because there's less neutral hydrogen gas in the center. It's either going to be molecular or ionized for the most part. So we get the neutral hydrogen mostly in the kind of edges of the disk, but we can see the rotation as a function of the flux as a function of velocity. The nice thing is this data cube has already been converted from wavelength space into velocity, so you don't have to do much there, but I do give you a little bit of some unit conversions that you can do to make this graph, make your graph slightly prettier. in terms of units, if you get to it. If you're working in the no AppFoat, you have a new version of AppFoat for ellipses. It's a little gross. Again, you don't really have to worry about what goes into it. The important thing is you put the center value for your ellipse in X and Y, then the width of the ellipse, the height of the ellipse, the angle of the ellipse, and your data. So I have done that. You just need to, when you go through your for loop, the only thing you have to change is where is your data. So you'll be getting data for each wavelength slice instead of just the one slice that I randomly pulled out in the 23rd position. So I think that's all I'm going to say. I'll go ahead and open up some breakout rooms for you to get started, but also, I guess before I do that, does anyone have any questions about? I'll be here, obviously, to answer questions if you do run into them as you get through. I am sure now that this is the last time we will be using float utils, so all the people who have been bouncing between my no float utils, that will no longer be an issue after today. But I think this is kind of fun to actually measure your own velocity curves for a nearby galaxy. So I wanted to let you do that before we abandon that frustrating program. Okay, I will get the mouse to work. There we go. Breakout rooms should be open so you guys can work, discuss together as you do, and I will, of course, be here to answer questions as you get through that. But this is where we will end today. So, and this is our main project for today.